Welcome. Thanks for joining us today. This is Nick Bilbitz with Veriphase. Today we're going to take a look at the core module of the ADT Pro Workflow Enhancement Suite, which is the SingleWeld module. SingleWeld is really designed to provide quick automatic processing of phased array weld data files. Then after processing, we'll see that there's several other benefits that can help you efficiently and reliably do the final analysis. If you watch the scan check video we did just prior to this, actually several of those features are built in, but they're in the reporting, which I'm going to skip over. We're going to cover reporting through the report updater data viewer video that we'll do in the future. So you'll see that then, but know that all those quality checks are available in the SingleWeld processing as well. We'll just touch on them at a later video. Really the real issue with manual analysis when it comes to phased array is it's obviously time consuming. Way too much time gets spent on all the tedious tasks that are required, like moving cursors, trying to find the highest amplitude spot, the 6 dB ends, changing the different displays, manually finding the same indication in every group, and then deciding which one to do the final analysis in. Really when you go to phased array weld analysis training, those tedious tasks aren't what your core expertise should be. Should be characterizing flaws, sizing flaws properly, and then applying reject and accept criteria. So SingleWeld tries to remove some of the more tedious tasks and really focuses the technician's training and expertise to the critical parts of the analysis. So what I've done today is I've chosen a file from a client. We actually went to a large manufacturing client, and they threw some qualification plates on us to test this software. So this is a 2-group 8-inch long scan. Again, it's a qualification plate they use to test their operators to see that they're able to do the analysis in that production facility. It is a double V, and it's 1.26 inches thick, so a little bit on the thicker side. Just going to dive into it. You can see kind of my laundry list there of why I don't like the pen and paper method, where you just start sorting through channels and you got to do all those things manually. By nature, humans are fallible, even though you're trained and certified. You could be under some stress, have some little data fatigue, working long hours. That can all affect your ability to reliably and efficiently analyze data. So this what I'm going to show you with SingleWeld is just a way to strengthen your analysis skills using smart digital software. So go ahead and start the ADT process. Looks like I already got it docked here. See SingleWeld, we've covered scan check in the past. Multi-weld is kind of its big brother, which we'll do its own video on. But let's go right into the SingleWeld. We really want to get down to the nitty-gritty, which is to quickly analyze and disposition this file. Choose the file I'm going to use here. The same kind of setup with scan check we've seen in previous videos is we try to minimize the amount of input, so everything's going to be digitally extracted from the file as possible. The weld overlay, the thickness, all the important processing parameters. So really I'm just going to tell it what I want. I'm just going to go right into OmniPC so I can do my final analysis. I'm going to auto adjust, so if there's any extra gain above scanning, we're able to take that out and bring it back down to reference as far as how ADT sees flaws or indications. There's some advanced and options that we can set in here, different ways we can view data, different sensitivity settings, different sizing methods. We're going to leave it pretty basic and just let SingleWeld do its default process for the purpose of this first video. So we're going to start processing this. It really shouldn't take that long. Again, it's only 2 groups, I think about 11 inches long. So it's done there, and it's actually popped OmniPC open for me. One of the great things is, if you're familiar with OmniPC, it's a really easy to use software, and we haven't complicated it. So there's no new learning for the ADT process. It's really just turn on the indication table, which I'm going to do in a second. But first I want to talk a little bit about the process, the pen and paper process. So without ADT, you obviously have a blank indication table. You have to start finding the view you want to use, start manipulating these data cursors, and really just trying to decide what's real, what's relevant, what's what's an indication, and then once I find an indication, I might write down everything I see in group 1. I might do the same thing for group 2, have to go all the way through this, what's real and relevant, what's the same indication as the other group. And this only gets more complicated as you have more groups. Thick weld like this, I'd probably use 4 groups. In this case, we only use 2, but anything over an inch, definitely. So it gets more complicated. You have more things to write down and try to correlate, and you're really left to not missing something or choosing the right channel. Once you find an indication, you obviously have to manipulate cursors left and right in every view, try to find the highest amplitude spot, and then you manipulate doing a lot of right click, left click, and then trying to find 6 dB or 3 dB drops, things like that. So it can be quite tedious if you have a number of flaws that you need to evaluate to your code or procedure. But we're going to show you right now how that gets much simpler. Right now we're in group 2. Let me go back to group 1. I'm just going to make sure the cursors are on, and I'm going to turn the indication table on. So unlike the without ADT process, once we've processed that with ADT, a few things to point out. We're working in a -ADT copy of that file, so we left the other one untouched, raw, compliant to code, good to give to your client. We're not going to manipulate that core file at any time. We're going to do all of our work. So that quick processing you saw of this file was 2 groups, and it was making a copy of the file, so it's very efficient in that aspect. Then we just came in and turned the indication table on. So down here it's a little bit different indication table. That's about the only difference. We add in some extra information ADT is able to tell us. We kind of have a VIN number. We call it a ref number. That kind of ties back to any reporting that we do. It makes each flaw like a snowflake, or each indication. We have an ADT score, which is kind of a confidence score. So we're able to set that in the software. By default, it's 75 to 100, and that's just a combination of all the algorithms working together. A very critical flaw in the middle of the weld that's obviously not geometry might have a very high score near 100. Something that could be cap geometry, but ADT sees it as different than other easy to rule out geometry in the file. It might score lower near that 75 type level. So that's an adjustable benchmark. We do normally operate with the default, at least when starting with a group of welds or a process, and it works efficiently. More hits doesn't necessarily mean more time. A very efficient process to get through them. So a little bit on that, and then you can see ADT actually adds in a bunch of comments, whether it's ID or OD connected, whether it's subsurface. Just allows you to kind of sort through these if you wanted to, and look at them in different ways, especially if you know what you're inspecting has a certain knack for ID or OD connected or subsurface type flaws. And then we've got all of these weld flaws, weld readings that we would normally see in ADT, or OmniPC, sorry. Things like amplitude, length, size, height, start, stop, all those things that help us characterize the defect, apply acceptance, reject criteria. And these are all pre-populated from the raw data, so it doesn't really matter how your technician set up the gate or how you set up the gate. We're looking at raw data, so we're going to pull these and be accurate on all of them. So a few things as we go through this. You'll notice if I click on an indication, we call this click and fly. So it's one of the most important features. We talked about the tedious aspect of trying to find the highest amplitude spot and then trying to find the 6 dB or 3 dB extents of a flaw in order to size it. When I click on this indication, all that's done for me. So we can see it's placed the data cursor in the highest amplitude spot in each one. It looks like we have a little manufactured ID crack here, a few different facets to it, and then we've placed the reference and measure cursor, so there's no more right click, left click, dragging that data cursor all the way through trying to find that needle in a haystack, you know, 1 dB higher, 1 dB lower, to make sure you characterize it correctly. This is done digitally, so we know it's going to be accurate. So that flaw, if I'm happy with it, I can move on. I could also, if I wanted to, obviously a 6 dB drop might not be the best way. If you want to size differently, the cursors are already put there for you, so you're already saving a bunch of time. But you can go in there and update that flaw. You can change that comment, wipe out the ADT comment if you wanted to. Just update it with the same comment for our purposes. So let's click on a few of these so you can get the feel. We go down to this one, we see a little indication there. This next one looks like it's very close to the sand axis. So this is another important thing. With all these populated, I kind of know what to expect. It's kind of a planned analysis. So there I hit on the same indication, but it's actually switched to group 2 for me now. So I'm able to see that flaw in both groups. I'm able to compare and contrast, decide which one I want to do my analysis on. I can see these next few ones are probably all the same flaw too. So there we get it in the second leg, but it's kind of a weak signal. Probably not going to analyze it there. I can just delete it and do my disposition as I go. Kind of the same thing, different little facet of it. Second leg. This one looks like the same thing. Get rid of all those. I'm down to these last two on the 5-inch scan position. Okay, that one's getting cut off. That one's a little bit better, not ideal. I might go back and manually look at that to make sure I size the flaw right. But we'll say we'll get rid of this one, and we'll keep that one for the final analysis. Go through this one. So just a real little, looks like small defect there. Kind of hard to see. And that guy there. So what I've been able to do is just click through from 0 to the end of the scan. Focus my attention on the real and relevant flaws, delete the ones that were duplicates, and get a good look at them in every channel without having to do manual group changes, manually finding highest amplitude spots, 6 dB sizing spots, and that's really it. That's the added value kind of that ADT puts into the analysis environment in a nutshell. Obviously, when you use it every day, you can sort, you can do a bunch of stuff. Depends on the file. This one's pretty short, so just having that focus me in on the relevant indications and do a lot of the tedious work for me. Saves me time and energy, and I can spend that time characterizing the defect instead of moving cursors around. So go ahead and close that. If you want to save a copy of it, you can, and later when we do the report updater, that's an important function, and we'll cover that. But this updated copy with your final analysis in it, any updated comments you put in, any deletions are gone. You could actually add new indications. You're going to be able to produce a final report on that, but that's a video for tomorrow.